I start off with, just for the rest of the day, a few slides on ConScape. And then I made an app where you can easily explore a couple of those parameters that we're talking about earlier. And then that'll allow you to get kind of as close to a CircuitScape style model as you can with ConScape, given the limitations that I set up on the app. Okay, so first, because this was going to start after lunch, I was going to do a review. But I jumped in all.
And do it as a quiz.
Yeah, exactly. Okay, so just to summarize a little bit of what we were talking earlier, why we think ConScape is a little bit better for these local scales as compared to this current density modeling is because of the way the paths are generated, right? They're not infinite and they're not random walk. So it's a little more biologically realistic, and they're computed between all possible pairs of pixels. And so you get a really detailed look at your environment, which, for instance, with the current density approaches, you tend to get more swaths and kind of broad scale patterns. So I think this is really the way to that. Okay. Okay. So why use ConScape? So ConScape was published 2022, 2023 by Brand Van Mortar. And it's a very cool thing. We've already talked a little bit about their advances. They talk about it being good for like large scale modeling and being very fast, but you need to understand that they're European. And their idea of large scale is a fraction of what is considered large scale in Canada. So their large scale is our small scale here. And it's great. So just to kind of summarize some things here, we've talked about a variety of programs and approaches towards modeling landscape connectivity, and they all have some aspects of habitat quality and structure and configuration in them. And they're not all equal though. So some of them are more biased towards and focus on the habitat side of things, like the equivalent connected area that we've heard about, and some are more sensitive to configuration, like current density modeling. I think ConScape is a really good balance between those two things, as well as including some aspects of ecological realism, like those movement behavior, like those path generations, as well as the distance scaling that make it a little bit easier to interpret in some ways, as well as a more holistic approach. So some advantages, it's very multi-purpose and flexible. So it's not just down to kind of the structural species agnostic connectivity modeling that we've been talking about. There's a lot more options. And again, computes paths between all possible pixels. This path distribution, it's not completely random, and it's not this optimal least cost path. It puts that on a spectrum, and you get to decide if you're closer to random or if you're closer to optimal, or if you're kind of in the middle. And for the most part, talking with the package creators and their trials and my own work, this kind of middle of the road approach seems to be best supported so far in these different cases. In terms of the path distribution. Again, these paths are finite related to dispersal. And in my opinion, I think those outputs that we talked about earlier, this functional connectivity, I find that easier to interpret and apply for decision making. So it's a very integrative approach and flexible, right? So what do I mean by flexibility? So if you're concerned with the habitat side of things, it can be as species specific or species agnostic as you like. We took the kind of simplest, most easily reproducible approach. But if you want to make something species specific, say you could use a habitat suitability map for your species at risk as your input for habitat quality, for example.
And that means you don't just have to have a binary map of what is habitat for that species and what is not, but it's like between 0 and 1. having any kind of measure of having quality that's going to be finding for your species.
And that can include climate, that can include different, land cover variables, whether the presence or absence of, types of trees or forest, whatever is important for your context.
Nice ask with it, you put in there, like a climate change, scenario, like a habitat for climate change, so you can, like the northern shifts, and you could, in theory, use this as a platform for a sort of more important scenario.
Yeah, so the question for the people online was, could you include some climate change prediction habitats as to do some scenario modeling using this habitat quality input? And absolutely. So if you wanted to say these grasslands and climate change are getting progressively drier and hotter, and so they're kind of creeping north a little bit. Yeah, you can absolutely be like, okay, this is under climate change. Worst case scenario 50 years from now, what does that look like? Run it through your model, create those maps, and compare it to your baseline.
Right. So you could actually, in theory, create an entire refugia map with future refugia being stored as
Yes.
quality habitat, whereas right now, not necessarily, but in 50, 100, 150.
So it's the input map of habitat quality, that you would outside of this, create those scenarios, and then use them as input.
Yeah.
Yeah, and that tends to be kind of where people get caught up the most in terms of the decision making around ConScape. It's just deciding which inputs are most important to include, and can we interpret this to use and accomplish our goals. So that's usually where the most trial and error goes into it. It's like, how do we build this data set, right? And especially if you want it to be reproducible or comparable across different landscapes, that's something you need to consider at that step. Onto our secondary inputs, permeability. This is even more flexible. So the simplest version is just this resistance space with this log transformation, which we've been talking about so far. It's very species agnostic. However, if you have more detailed information, like observed movement data, you can create like a probability of movement map. Or if you have mortality data, you can map out survivorship as well. And so there's all kinds of interesting things that you can do with that. And I'm very unfamiliar with those approaches, but I do know that it's possible and for them.
So that means you can directly kind of, more or less directly input tracking data. Right?
Exactly. Yeah.
Halfway.
Mm-hmm. Yeah. So in a kind of traditional species specific approach, your inputs would be habitat suitability map specific to your species. And then ideally, if you have observed movement data, presence, absence, abundance data, whatever, you can create a kind of distribution map of that as well and infer permeability from that. Okay.
Now, there's a little bit of a potential for confusion here because of terminology.
Yeah.
I talk in the morning, I talked about these landscape permeability versus the habitat focus. So I use it as landscape permeability as like the multiple fault. And here it is like the permeability of the cell, like it's more like the opposite of resistance. If it is has a high resistance, it's bolder, or like it's become the silver belt. So it's the term is used differently. And what we see, I think in the end, those two maps that are shown, they're the same thing, because when you have high habitat quality, now they have high permeability, that means low resistance. So you could start with just feeding up the same map for both parts.
Yeah. And that's something that I was talking with Grant, the package creator, about, because he's still kind of like, yeah, I don't know if I have a better word for this because it's already so pervasive through landscape activity work, and it's not exactly the same thing, but also this input can be used for such a wide variety that it's like, how do we name it? So the terminology
Resistance there with the tracking data and the survival data.
doesn't make sense. Yeah. Awesome. Did you raise it?
Yeah, just a question about in this context. So I was thinking of conductance.
Yes.
Focus, yeah. It's variability. You can just contrast between the use of a resistance layer versus a conductance layer for this purpose.
Because one is the inverse of the other.
Yeah,
Like whether you use then a one over, like conductance is one over resistance and the other way around, or some other function. This allows you to specify that function. So again, it's more flexible. And that means we cannot give a simple answer to this.
yeah. Exactly. Yeah, the answer to all of your questions from here on out is probably gonna be it depends.
It's your choice.
Yeah, exactly. Alright, so then we have our two outputs. I already talked a little bit about functionally connected habitats and these movement flow maps. And so I really like the habitat functionality maps because they give you this kind of blended hybridized view of like habitat focus and configuration focus, which I think is a really good thing for application. Okay, so moving on to some of those parameters that we were talking about earlier about these paths distributions. So we have these kind of, so far, binary approaches, like current density, which is entirely random movement, okay? Versus something like least cost path, which is just the optimal path between 2 points, okay? So this parameter theta within ConScape allows us to be anywhere we want on this spectrum in between there, okay? So least cost path modeling, it's identifying this optimal route between these 2 points. And it's like, that's a good thing to know. It's very simple to use, it's simple to calculate, or it's not very biologically realistic in most situations. Unless you have a particular animal that has very set movement behaviors, most are not going to follow this pattern. Okay? However, on the opposite end of the spectrum, we have something like circuitscape or density modeling, where you have entirely random movement from these 2 points, and you consider all possible paths in between. And that's also not necessarily realistic, because we know that animals don't move entirely randomly either. Okay? So being somewhere here is a lot more realistic in terms of animal. And so theoretically, you can get ConScape as close as you want to this random movement, as close as you can to current density modeling, if you reduce this data all the way to recreate this kind of random movement. So Neela, when you were talking earlier about like, can you do those comparisons? To make it kind of as fair as possible, you would want to be on this side for ConScape to compare it to circuitscape. And so this is just between 2 points. You can do this if you're not considering this opposite side in ConScape. But for the most part, we're really concerned with the entire study area. So paths between all possible pairs of pixels. And so that would look something like this, where you have more toward the least cost path side, you have this kind of spready habitat effect over here. And then as you widen out that path distribution, you see the expansion of that functional habitat.
So this is now the ecological flow part, right? So you don't have that now.
They both use
So
the
you're
data.
going down there now. What do
And I did some long ago, I honestly don't remember. But you will see,
I think so.
you'll see similar patterns. Whether you're doing functional habitats and comparing as you change data, or if you're doing movement flow maps and you change data. And that's something you can explore in the app in just a few minutes as well.
That's the
So-
first exercise.
Yes, remind me of that in 10 minutes.
So is this what, like, is it doing like a wall, like, where is the current being projected in this model? Is it the,
So when I say that the paths are computed between every possible pair of pixels, that means in like a circuitscape mindset,
yeah,
every single pixel is both a source and a sink.
Oh, okay, okay, oh,
Okay.
yes. That's,
I was gonna say that.
There we go.
Take a while.
Got it. Yeah.
but then these paths are gonna be weighted by the quality of the source, like, as part of the endpoint.
Yes, yeah, yeah.
So you wanna know how much, like, the connection, how much does the cell from net could become. And so that.
Yeah, and as you'll see, once we get into the coding section, we can kind of quantify that functionally connected habitat as well, like put a number as a percentage on it, which is kind of cool. So that is, if the entire study area was, perfect habitat and it was all perfectly connected, then that number would be 100%. And of course, it never is. So we can create that reference and quantify that for decision making, which is cool.
Which is again similar to the indicator of that equivalent connected area as a compared to reference. That's what that could reach.
Okay. So now on secondary kind of biological realism part on this dispersal distance. Okay, so the paths and kind of habitat, everything is scaled to this parameter called alpha, which you said is related to dispersal. So it's not a set number, it's a function. And you can specify that and how it's scaled by this parameter alpha. So by far, like the default is a negative exponential. Is okay, yes. So unless you have kind of strong biological reason to not use that and use something else, I would suggest using this. And so similarly, this alpha parameter, you can see if you have really low dispersal, you have a really limited available habitat, right? But as you increase that, you see this area really expands. Okay?
And especially the numbers go up.
Yes, that's an important thing to keep track of the maximum value on this scale. Okay.
So 160 is the maximum of the left. 4,000 in the middle and
9,000.
yeah. It goes in the back.
Since it's going from every pixel to every pixel, does it like prioritize what defines to be the best habitat as the best smallest area? You know what I mean? Like why are these bright green spots not the same in all of the maps? Like, why is it not more random?
So at least for the functionally connected habitat, you have, for each pixel, you're calculating this value, right? And that takes into account not only the habitat at that pixel, but also the habitat and how well connected it is in a surrounding area around it. Okay? And so that's all weighted.
Changing them.
And so think of it as kind of a moving window for each pixel.
Yeah. So think of it like this Gaussian curve that is
Yes.
centered on yourself. And so the maximum value that the high quality habitat that is X meters away have depends on how far that curve. If it's far away, it will contribute a little, just only a little bit, and if it's just next to you, it contributes a lot. And then, of course, then that's the maximum you could get if you have an equality 1, but if that other pixel has a habit equality 7, you multiply the whole thing by.
So you had a question?
Yeah, it's usually moving inwards.
It's easy.
Moving inwards. When kind of, but that's really like usually favorites is the area of time. So
Not necessarily. Because it's also taking into account, it would be the question. Yes, sorry. So this question was, if it's using this kind of kernel approach by pixel, does it typically favor the center of your study area?
Well, that automatically happens because then you don't have at the edge, you don't have that much. It could be connected to, so that's
Yeah.
where you have boundary.
Yeah, outside of the boundary effects. But
So
Yes
in
or
this
no?
case, would you add that buffer beyond the study area as well to kind of
Yeah.
support
Exactly, yeah. So this is, the example study area that they give in the paper that I was playing with the data. But yeah, you should have a buffer around that area.
It should be at least as far as your alpha thing. Yeah.
Mhm. Does that help? Okay. Okay, so, depending on these two parameters, alpha and theta, you could create quite a variety of maps. Okay, so, let's do. Okay, so here you have low dispersal and then nearly least cost path. You have an intermediate value, and then we have nearly random walk here. So this is very similar to what we just saw. So now we can compare that if we add slightly higher dispersal, and we can see how these maps change this way as well as we dispersal, and make this a really wide variety here. And now, from an application perspective, you're like, okay, how do I know what's best? How do I know which map is the most appropriate for me? And the best way to do that is to test them with animal data and validate them. Okay. If for whatever reason you don't have the time and resources or computational ability to do that, the ConScape authors suggest and have found in previous studies that intermediate values of both your dispersal and theta are typically the best supported. So ideally, you can do some kind of model comparisons and selection. But if for whatever reason that's not possible, kind of go with the middle of the road approach as a default setting, sort of. Yes,
Is this like a simulated landscape or that's a?
this is real. This is in Norway. It's a reindeer map from Norway that the authors were testing on.
Because I just was curious about the. This barrier. Line that's in the middle,
These,
that shows when you increase movement, but it's not there kind of when you look at it from the east perspective. So there is a barrier there.
well, I think
Well, it's there,
it's
but there is a lot.
there. There's just so much else dark that you can't really identify this area. Like it's still dark here, it's still dark here, it's still dark here, but because the rest of the habitat is bright on either side, you can be like, oh, this is a barrier. This could be a river or a road or something. Versus over here, you wouldn't know. Because it's just all so dark. Does that make sense? Okay.
So a lot of it is the visualization, but what I see here is where the top big and low, doesn't make a huge difference. It makes a difference in the intensity, that means like the maximum value of the statement. But if you just look relative, when do I have low values, it's similar, relatively similar pattern. If you go from left to middle to the right, you have huge differences. And that, like, is this now the flow part or the habitat part? Because if you go to the random walk, I think it's the flow part, this one. Right? And as you go to the random walk,
Yes.
you end up recreating the habitat, like the functional habitat map. And that's what I said in the morning. Oh, you know, they're not two different things. It depends on our assumptions. One will turn into the other. And now, when we do the exercise, that will become clearer to you.
Yes. And so we'll get to that a little bit right now. So the data set that I've put together for you guys to play with is in the southeast corner of Alberta. Okay, and this is some stuff that we're working on for the Prairie Conservation Forum, kind of mapping out structural connectivity of grasslands in this region. And so this is the border runs to the US and border over here. So you got Medicine Hat, the river, Lethbridge is just outside. So that's kind of oriented there. And then we can play with, and you'll be doing some very coarse resolution generation of these maps later. But they will look like this, where you have functional habitats, and this is that should say movement flow on the right side. And yeah, to make sure that it's, runs quickly on your laptops. This is at 2 kilometer resolution. So each pixel here is 2 kilometers by 2 kilometers. And the maps that I'm showing here are beta 0.5, which is a recommended kind of default middle of the road setting. And alpha 1/75, which is a pretty generous dispersal distance for this given setup.
Does that mean like it can go 75 cells?
No, it's a scaling parameter for that distance function, so you can't really interpret it directly like that.
Then there must be some interpretation. Like if you look at the 75, the one over part, that like the bigger that one is, the longer distance you're dispersed.
Yeah,
So yeah, a question about that. How would you interpret that alpha value to an IR to be like this? 10 kilometers?
Yes. So, because it's the alpha, it's not a direct value, it's a scaling parameter for a function. And it's not quite ready yet, but I do have an R notebook that kind of walks you through that process. Because, for example, we were running into that issue earlier. We're like, okay, how do we make this appropriate for mule deer or for badger or something? So for example, like in the literature in Western Canada, they say average dispersal for badger is like, what was it, like 9 kilometers, something like that. Like, okay, so we need to basically plug whatever we can into this equation and solve for a scaling parameter alpha. So it's kind of that situation. It's not in map units, it's in pixels. So if you change the resolution of your map, you'll need to change your alpha to make sure that it maps. And so it's usually a negative log distance. So you're thinking about this relationship like this. You say, okay, now I want 50% of my signal to remain at this 10 kilometer mark. So then I use my alpha to change this steep curve into something where that 50% under the curve occurs at that 10 kilometer. And so, yeah, there will be a notebook coming out that will help you solve for appropriate alpha at some point.
But this could be something if you, I think it's M that is the power of what, and then you tool that's the standard. And then if you have, it may be that this 75 now means that the median dispersal distance is 75 times your cell size. That would be 150 kilometers. Could be, right? Something like that.
Yeah, I don't remember off the top of my head. I need to dig into the.
I don't know whether it's the 95% or it's the median or whatever it is. It's been, the documentation is not good. We don't see the underlying code, so, yeah. I've been struggling a bit in the details of that.
Yeah, but we think we're getting there, and there will be documentation work at some point in the future. And I've been kind of in contact with the authors, and I told them what we're doing today, and they're very excited, and it's kind of like remotivating them to be like, yeah, okay, let's get back on this, and make it a little easier for people to use. So, hopefully, this helps as well with people's understanding of the program. Okay, so now let's go ahead and take a look at the app. So this link was emailed to you with the rest of the workshop materials, and last I checked, it was still working. So the easiest way to open the app is to just click this link and open it in your browser. Okay, and you should see something like this here. So I'll give you guys just a moment to do that. So I'll take a pause. So this is basically just a viewer to help you compare and take a look at how these alpha and theta values affect the maps. So you have these drop-down menus here, select raster type, select theta, select alpha. So raster type, you have functional habitat maps, which are in the green and blue. Then you have movement flow maps, which are in the more purple and yellow. And then you have select theta and select alpha for I think 5 values. So there's a bunch of different combinations that you can make here. And to help you two guys started, and guide your thinking on this a little bit. We want to, I think a good place to start is explore and compare the extremes of the parameters for both functional habitat and mean and flow. Okay, so some things to remember. Well, not remember because you're learning it for the first time. Low theta values indicate random movement. So like a 0.00001 would be like almost entirely random walk and as close to this current density style as you get, versus the higher theta values are closer to this plus path. And now with ConScape, when you're generating these maps, if you set any of those parameters too extreme to the point where it's affecting kind of how the subnetworks are calculated, it'll throw an error and tell you, be like, hey, this matrix isn't looking right, change your parameter. Okay, but all of these maps are pre-made, so you won't see that now because you're just viewing them, you're not calculating them. Okay. So the first comparison, let's take a look at the most restricted versus the most unrestricted map. So let's do it for functional habitat first and then movement flow. So what I mean by most restricted is just set your theta to the highest level in your drop-down menu. So that's the closest to least cost path that you can see. And then set your alpha S to the highest value as well, because it's reversed in this situation where low alphas indicate higher dispersal. So we want to restrict that as much as possible to get our kind of smallest habitat now. Okay. And then here's the yes. So high theta means least cost path movement, and high alpha means really restricted dispersal. And then for your stiffness.
A quick question about the parameters. So theta, what is it bounded by? It's going.
So
up.
0 to infinity.
Okay.
Yeah, but you won't get past 5 realistically.
Okay.
You'll probably get errors around there. So I stopped at I think like 3 or something.
Okay.
So it's not extreme, but
Okay.
Yeah.
And then alpha doesn't.
0 is being like no dispersal.
Right.
It's to the size of your study area, whatever is realistic,
Right. Okay.
right? Or yeah, that scaling parameter with that function would be like 100% of your paths across the entirety of the study area,
Right.
which kind of makes
And
sense
now
for that. No, I just selected, something reasonable. So, yeah, then most unrestricted, low alpha, low theta. So you can do that for both the functional habitat maps and the movement flow maps. Take a look. Right, and then when you're done with that, take a look at the other extreme options. So kind of mix and match your extremes. And say, okay, now that we have those extremes, how do they compare to the most restricted to the most unrestricted, or kind of this middle of the road approach where you select a moderate value for both? So now I'm going to stop talking for a little bit and let you guys play with this, discuss with the people around you, ask questions, and I'll just be around for a few minutes. We're going to talk a little bit about these maps.
Like a more guided exploration. Hopefully it will fit with what you've been exploring and help you make some more sense of it. Because there's so many things you can change here, right? So here we have chosen functional habitat on the left map and movement flow on the right map. And then the same settings for theta and alpha in both maps. So we're looking at one kind of parameter setting and comparing the two maps. On the left, the map of functionally connected habitat, and on the right, the map of the flow. And we see we have a lot of like high levels of functionally connected habitat in the southeast, southeast border here of the province, and also that's where we have the highest flow happening. The settings here is an intermediate value for theta, the 1, not like between 0.1 and the 3 kind of, and it's the alpha is also an intermediate value. So now what happens if we go second to 3, that is random walk, right? Or the other way around?
Is it lower?
That is, okay, so random walk would be a low value.
Yes.
But we change that here to random walk and we keep the same alpha. What happens now is that the flow map doesn't look like a flow map anymore. It doesn't have those pathways, but because it can flow everywhere, it really tracks the other map. And if we had used the same color scheme, these two maps would look very similar. So when we go to the random walk, that a movement flow map becomes a map of our functionally connected habitat. If we go the other direction, where we go to the least cost path, that would be here the value 3. We don't see it that well, but kind of we go a little bit the other way, other direction.
Yeah, if you go too extreme down the like increasing theta by too much, ConScape will give you some errors because of how it's like the subnetworks are calculated in that. If there's too many like disconnected submaps, it'll throw an error and tell you like, hey, this isn't quite working. So using ConScape for least cost path type modeling is generally not recommended if you go too far to that extreme. So that's why like you can get current density type looking maps here, but least cost path type maps doesn't really make sense in a graph network type situation.
So we're back to kind of these intermediate values where we have two somewhat different maps. And we've learned that if we choose a very little small theta, which means pretty much a random walk, we get from a movement map to a habitat map. What else we explore? So then we can look just at the effect of alpha. We keep that intermediate value of theta and now we look at the extremes of alpha, very restricted and very large distance, and I need to change these now to the same thing, functional habitat. Is it very restricted? Is that correct? Certainly one. That's like oh,
So yeah, no, that's the most restricted. Yes.
that's the most restricted. Ah, okay,
So
so
it's not like extremely
Yeah.
restricted, but comparatively so.
but like a cell here is not really connected to a cell in another part of this study area. Whereas here, they are kind of much more connected across larger distances. Is that what we're seeing?
Yes, exactly.
Yeah.
So this one would be a functional habitat map for an animal that can travel large distances very easily. And so it can make use of all of this. And from that organism's perspective, this landscape is very well connected. Versus if you take a species that has much more restricted dispersal and from that perspective, this landscape is not very well connected, right? You just have this kind of hotspot here. And like, if you're lucky over time, maybe you can travel this way, but it's generally very much more restricted if you pick one spot.
So now this map on the right, which is the flow, movement flow map. Sorry, this is.
Oh,
the
and
functional
also
habitat.
pay attention to the maximum values here. This one max is 200 and this one is 4,000.
Yeah, so with this kind of. Okay, unrestricted dispersal, any habitat is reachable. And that's why we get everything is kind of yellow. It's everything that is good quality habitat is connected to everything that is good quality habitat. It becomes just your habitat map, not your habitat quality. Yeah, so not the
Exactly.
functional. map,
It
but-
resembles your input habitat quality.
Exactly, yeah. This becomes your input habitat map more or less.
So, following up on what you just explained, I was thinking of something else, like in terms of as time goes by and then if you are lucky enough for the habitat of the matches can support you to move from this batch to this batch, given your dispersal ability to move from this one to this one, there's also like if we think from like the random stuff, there's also step and the step direction.
Yeah.
Right? Is there a parameter here that you can control step direction? Like, can you, for example, set some movement with this person if like it's more likely or like a probability surface of when you encounter a more usable character based on the different layers that you put to the programs. Can you, for example, set a rule that use these cells first?
No.
With this direction.
So in not as the, you can't change easily, at least the, algorithm that's generating the random paths in ConScape. So in terms of direction, it's computing like, paths between this pixel and this pixel, they're kind of going to be going in that direction generally. If you have specific movement data of saying, hey, I know that these animals are more likely to move this route, you can put that input in your input permeability map, and that will help facilitate that movement because it's kind of like almost a priori knowledge almost. Right, so that would be kind of the best way, I think, to include that information into ConScape. That's personally the MCMC algorithm that they use to generate those paths. I don't know very much about how it works and I wouldn't mess with it. But I do know that one thing, the paths can also like self-rescue. So if you are looking to go from here to here, there's a chance that you'll get part way and just decide to stop. So like, this is good habitat, I'm gonna live here now. Right. And so not all the paths are guaranteed to make it. So some will just die, some will stop part way. And that's part of the random output.
See, the values on the right, are they just relative to each other, but compared skill changing, play around, is that? Just think of that as relative to each other, or doing something.
So they're kind of functional habitat scores where it's representing, it's like a weighted value. And in terms of absolute values, because these maps were generated with the exact same input data, I would say they're somewhat comparable.
I think the values have some meaning in terms of analogous to the equivalent connected area. But what the units are, we cannot explain at this point. We don't
have a biological
figured it out.
unit.
It
Yeah.
may, but
Yeah,
we
in terms
can't
of
tell you.
quantifying that, we'll see that in the code. And you'll get like a percentage of what percent of this landscape is considered functionally connected habitat.
That's what you mean by they're comparable.
Yeah, so you would use that other metric to compare between scenarios and situations. These scales are just for reference and visualization. But we should probably wrap this up.
Yes.
Yes. Okay, so in the interest of time, we're gonna move on to the coding aspect of this lab. So, yeah, can you see this? So, in the last part of this workshop, I'll be going through the coding section. I'm gonna be going through the notebook up here, rather than running it like with you on the laptop, because this thing is ancient and in, addition to running that and sharing screen and the laptop I upload. So, you have a couple options. If you don't want to run things locally, you can open the, see what's it called? Like LC Connectivity Workshop Part 2.html in your browser. And you can follow along in the notebook that way. Or if you prefer to run things locally on your computer, you can open up the .rproj file on your computer, and that should open up that instance of RStudio, and you can run through things there, assuming you were able to get everything downloaded and installed properly, which is the hardest part for this situation. You guys got things open. Can you give me a little signal as if we're good to go? Seeing some hands. Okay, cool. So I'm just curious, how many of you are gonna attempt to run it along with us locally on your computer? In our studio, a couple? Okay. Cool. If there's time, I might be able to help you if you run into errors or anything. But I did have me know me to guinea pig test on this, so it should run without errors if you have everything set up. Okay. So
Can you repeat where to open?
I would recommend going into the workshop part 2 data coding folder and then opening the .art file, because that will open up and then all of your paths should be good from there. And then once you're in our studio, open up the .rmd.
You can just get started. We'll catch up.
All right, cool. So first thing in R is importing all the packages that you need, which you'll do with the library command. So library ConScape R. And then we have this other line here, ConScape R underscore setup. This dot get environment to the path. So this means that you should have already, hopefully before coming here today, integrated a path to Julia installation into your R environment. Okay, and that is because ConScape R is a wrapper program. So the base ConScape program actually runs in Julia, but because the limited amount of coding that us ecologists tend to do is usually in R or maybe Python, and Julia's a bit of a jump. And so they made this wrapper, which allows us to code in our studio while everything kind of secretly runs in Julia behind the scenes, and we don't have to worry about it. Okay, and so that's what that is. And then the normal R packages that we need are Terra SF here, which helps us get the paths right to our files, data flyers, TMAP for visualization, and this GDL utility. You might also need package Viridis. Okay. So if you open HTML in like Brave or Chrome or something, you should get a nice little toggleable table of contents. Because Teams, I'm on the browser and it doesn't allow you to share screen using Brave, which is what I have. I had to open it here, so I don't have that table of contents, but you should. So the first chunk of this notebook, we're going to be talking about data preparation and kind of the most simple step. And so I'm going to be showing you this naturalness, how we created that naturalness input map from the ABMI's human footprint inventory. So we need to first import a bunch of data that we're going to be using into our environment, into ConScape, and so this network representation of the landscape consists of 4 parameters. We have the likelihood of movement between 2 adjacent nodes or pixels, the cost of movement between nodes, the suitability of pixel as a source node and a target node. So that's when we refer to nodes in ConScape, basically every pixel is a node. It's both a source and a sink. And that sounds like a lot of parameters to worry about, but we're going to simplify them a lot. So you don't have to worry about it too much. Okay, so this first file that we're reading in, AOI, area of interest, it's just the boundary of the study area that we're interested in. So, all right, what we're doing in this is we're taking publicly available data from the ABMI, the Human Footprint Inventory, and we're preparing it for use in ConScape. We'll then use ConScape and we'll create those functionally connected habitat and movement flow maps. And then we will also do a little bit of scenario modeling in simulating restoration, where we have a patch A and a patch B, and then we'll use ConScape to compare those situations, be like, which one should we restore? Is one better than the other? Okay. And then there's some optional code at the end with some additional exercises looking at movement flow and syncing files and such. Okay. So first thing we do first is loading our packages. We're doing some a bit. Okay. And then I'm not just gonna read this text.
Just skip that
Out
part, I
here.
think.
You can read on your own. So, we're defining our habitat quality as habitat naturalness. And so we're gonna walk you through that. And so first, we want to extract human footprint data from that geodatabase that you can download from the ABMI's website. And it's faster to do that if you use this vector style thing. So you set this F as the path to that geodatabase file, and then you vector it using this proxy. And then we want to read in our polygon shape file that delineates our study area. And for your study area, if you want to do this on your own, you can draw that in ArcGIS and then just export it and load it in, and that's fine. Okay, and then we need to take that polygon of our area of interest and basically create a raster version template of it, which is what this template and then R_AOI is. And we use this fasterized package, which hasn't been updated to work with Terra very well. So that's why you see it's like raster, fasterize, and then Terra rast. So it's basically creating those different things and formatting it so it works properly. Okay. And then we have a prepared base map for visualization. You can get that from Google Maps, from Leaflet, from ArcGIS, anywhere you want. And we view that study area. So this is mapped using TMap, which we quite like for visualization. So you've already seen this study area in the southeast corner of Alberta. We have Medicine Hat in the north up here. So now our main goal is we want to extract that human footprint data within that study area. Okay. And we want to convert that into a simple feature or multi-polygon object. So first, we need to query that vectorized path to that database that we're talking about to the extent of our raster template of this area of interest.
So we're extracting all the vector data
Within that,
of the human footprint within our study area.
exactly. Yep. And then we do this little conversion, so STSFF, and that puts it into the simple features package object type, which makes it easier for us to look at later. So then you'll get this output. If you look at this object, human footprint 2021.
So why are you using 2021 as it's 20? Is that always different?
No, yeah, because it's, when we created this, that one hadn't come out yet. And I didn't update the code. So you can use any version of that you want. We're just using the one slightly out of date. And then you get some output showing all of those polygons. Okay, and now some issues you might run into. You shouldn't for this data set, but you might, if you're doing this for a different area on your own, is running into polygons that don't close completely. So when you have this kind of multi-polygon file and then you extract it, sometimes there's an issue where those polygons don't close properly and you have this weird like linear features in your polygon and it doesn't, like, R doesn't like that and it just continually throws errors. And so you have this little function that Helen wrote.
No, I found it in me.
You found it somewhere?
Somebody's the oil.
Somebody wrote it and it works, so feel free to use it. Okay, and that ensures kind of complete multi-polygons. And additionally, the SF package has another checking for your data function called stMakeValid, which will let you know if it's considered valid. So your data should pass both of those checks. Otherwise, you might have to go back and see what's going on there. And yeah, the data for this tutorial should pass both of those, no problem. But I thought it would be important to include that code for people who want to try it on their own study areas in the future. Okay, so now we have this human footprint inventory extracted to our study area, and now we need to convert that into naturalness. Okay. So we have these use and footprint values, so UF values. And this information was taken from the Merrick et al. Paper that Hassan was talking about earlier. So these values were pre-created and are available online. And I also leave them in this image here. So these, you can see here, we have North F, North U, North, South F, South U. And that's because the values that they determined for the different polygon types were dependent on whether it was in the northern part or the southern part.
Silver meaning like.
Forest
dominated,
versus-
Yeah,
Yeah, forest, like boreal forest versus everything else.
like green area, white area.
Exactly. And so our study area for this is completely in the south, and so we'll just be looking at those columns. But first, another data check. And we need to make sure that the human footprint categories in our map are all represented in the UF file that we imported. And so we have a couple little things here to check for that. So making sure that all of the elements in table is element unique. Human footprint 2021 feature type matches all of them in the UF values.
So something that could happen if they now introduce, they also mapped solar farm. That was not in that list. Then you would have non-zero in there, but it would show up solar farm because that would the value.
Yeah, and then to fix that, you would go into that file and you would have to basically create a value for those solar farms. And you can, talk to somebody to get an estimate for that, or you can make something up on your own, or just based on whatever's closest to the map. Okay. And then this set div, it says character 0, but if you did have an element that needed to be added, what that would do is it would print that out for you. So that first one just tells you, okay, how many are not included? Like, do you have any falses in that? And then if so, what are they called? So you can actually go fix it. And then what we do here is we are adding the little data manipulation where basically we have this South F and South U values, and we are adding that from the UF value data set onto our human footprint inventory data set.
As that into the attribute table.
Yes.
Yeah.
Exactly. All right, is everybody following so far? Okay. Okay. Now, one line that we added to those UF values was natural, right? So we define that here, where we create this area of interest feature, where we take our area of interest study area polygon, and we add a line to that attribute table. And we say feature type is considered natural. And the important thing here is that the resistance values that we're looking at are 0 and 0 for human use and human footprint. So it's saying
Total absence of any map footprint. That is not like missing value, but that is actually kind of
yes,
fixed having quality.
yes. So in the human footprint inventory map, you have these polygons on top of nothing, right? And so what we want to do is we want to create a background of natural and then put those polygons on top of it and assign them values. Okay. And so that's what we're doing here. Right, so we add that, we create it to be a feature with a geome, and then bind that to our footprint. So now we have our data cleaned and valid and organized. Now we can actually do some calculations here. So we want to calculate two new variables, H, which is like standing for a combined human footprint, where we're taking the average human use and human footprint value. Okay, so that is representing this combined deviation from naturalness. Okay, and then we create our habitat quality, our naturalness, by just doing 1 minus that value. Is everybody, I'm seeing some confused looks here. So
So that wouldn't be necessary, but if all this could use for quality, then we know that's the input we will not have or the happen.
So all of the human footprint, intensity of use and use values that we imported in that US values, they're all between 0 and 1. And so we take the average of that with higher values representing more intense human footprint. And then if we want to reverse that and say, how natural is it? We do 1 minus that. And if there's no polygons there, there's no human footprint, we're left with this value of 1. And if you have a really intense human footprint, 1 minus that larger number will create a value nearer to 0. So that's how we're setting that scale from 0 being, completely human altered landscape versus 1 being completely absent of human influence. And then it gives you a bunch of outputs. And then now that is all in polygon format, and we want to convert it to raster. And so that's what we're doing here. And that's basically creating a stack of your different polygon layers on top of each other. Sometimes they overlap, sometimes they don't. And so to merge it all into one nice big flat raster layer, we do this fuzzy algebraic sum where you want to combine the Q values for those pixels that have fixed values. Is that an accurate description of fuzzy algebraic sum?
Yeah, it's not just the mean, but it's like you will have multiple ones, but it will be at least as high as the highest individual. So if your highest
So in case your polygon layers don't perfectly mosaic, it's merging those kind of overlaps nicely.
Takes into consideration area.
Sorry?
Does it take into consideration the values and the area when if you're trying to come up with a?
No, it doesn't. I think clearly it doesn't, no. And I think something's wrong here because it should be done with the age and not with the. But anyways, so we may need to update this and double check the update. But this is not like this, because by the way someone using this is with 10 meter resolution across the province. And then you aggregate that to 180 waves on the stuff. So with 10 meter, there is not that much mixed. So it's just everything that occurs within those 10 meters is
Based on like the area. Or
no, just if it is present, it is
so if,
not the amount of area.
so what if you have like a low, like low square polygon bicycle?
They overlap, right? But you have a cell of only 10 by 10 meters, then you won't have too much overlap because in the 10 meters you won't like you won't have too many that operate only part of that picture. So we just take all the values, all those that are present here, and do that everything that
Yeah, that sounds right.
fuzzy mean. The fuzzy mean, so in terms of the human footprint value, that will be at least as high as the highest individual value. So if your highest human footprint is already 100%, you can't go higher. But if your highest one is 50%, then there's another one 20%, you might end up with a 55, 60%, something like that. That's the thing. That's it. Fuzzy mean thing. So it cannot go lower at that height you have, but it can become higher because you're stacking. So that is now really detect on details. And this could be done differently, but in a way that helps you see how the other these current things were done.
And we're expecting at 100 meter resolution as a baseline, so we'll have, I think, less overlap than the 10 meter resolution that you mentioned before.
Now there's going to be more, this
Maybe.
well, edit this is a draft file, and we plan to kind of edit that, like have a bit more explanations and stuff. So we'll work on that.
That's a good point. You guys are guinea pigs because we haven't tried to teach this to anyone before. So feedback on like what's confusing and how we can improve this will be super helpful.
Is fraud a function already in the car that does that fuzzy alpha stuff?
That's a Helen question.
What the function is?
This here.
Yes. Yes, but you have now we have a stack that has like as many layers as there is human footprints. And that's something. And it will take the product of each one of those. Oh, it can be choose correct because you would do 1 minus each and for the product. And we already defined Q as 1 minus H. So now we can just take the product of all those, the whole stack. Yeah. Kind of efficient or programming. But that will need a little bit of more explanation. Those who want more stack approach.
So then that's the last step of creating this nice natural habitat map here. And we can see that again, this is at 100 meter resolution right now. And it's looking pretty good. We have a little bit outside of our study area here because of how that human footprint extraction works, is that it uses the extent and not the actual border. So we'll clean that up in a minute. So then we have our quality map here. And if you had like a different goal for permeability, you could generate that from completely different data. We're using a very simple approach where we're just creating a resistance map directly from our quality map, just with this simple log transformation here, where we're taking, so this quality map is called Q now, and we're now calling R, which is the log transformation 2 minus Q to the power of 10.
And how resistance value?
Resistance values.
Yeah.
Yes, exactly. And right now Q is on a scale from 0 to 1, so we need to have that 2 in there because logging 0 doesn't really work.
So what happens if quality is highest, it's a 1, right? Then we have 2 minus 1 is 1. 1 to the power of 10 is the 1.
Yes.
If we have like the lowest possible habitat quality, we end up with 2 minus 0. That means 2 to the power of 10, which is 1,024.
Yep, that's here. We have the range of values shown. And so now if we plot R, we see it as kind of the inverse of that habitat quality map, where we have lots of really low resistance and some middle ground over here. And then like medicine map, for example, is really built up. You have really high resistance values there.
And the highway.
Yeah, you can kind of see the highway, which is impressive at this resolution. So that's cool. I guess no, we're still at 100 meters. Anyway, okay, so now we need to clean up our maps a little bit. So we want to crop them to our study area. And again, you know, we're just accepting kind of the boundary anomalies in this situation. You would normally put up a buffer, and I skipped that step here. Okay, so we set the coordinate reference systems of our new maps to our input data, and they're all extracted on the same like NAD10, UTM forest, whatever the AVMI uses is what all of this is. Okay, and then to make sure that it runs quick on your computers, we use this. We use the prompt and then AOI mask equals true. So that's going to get rid of that data outside of our study area. And then now that they're cleaned up, we can aggregate them to a much coarser resolution. So these maps run quickly on your laptops. So that's what this guy is here. We have resistance.2000 equals Terra aggregate our resistance map by a factor of 20. So that is our 100 meter resolution times its factor of 20 equals a 2000 meter resolution in output. And then we do the same thing for Q. And then we stack those rasters. That step is optional. You don't actually need to do that. But for the sake of visualization, in this next step, I did that. Okay. And so you can kind of see how these maps are just opposite, right? So this resistance, it's not adding a ton of new information to this because we're in the simplest situation where we essentially have one input. But that's not necessarily the case for every ConScape situation, right? It can be created permeability maps from observation of movement or survivorship or whatever you want. But we wanted to get you guys up and running with like the simplest, most easily reproducible situation. Then there's some code to save your rasters to a TIFF file if you want. Then, if you skipped the download of that human footprint inventory, because it was like 3.5 gigabytes or something, you can just jump here because we saved those, these resistance and quality maps for you as well. So you can just import them directly if you want.
That removes the hashtags, so that means I've told COVID, but
Yes. Okay, I need to speed up a little bit. Okay. Now that we get to the good part, I have to know. Okay, so running ConScape. We mentioned earlier that ConScape kind of runs off of these four values. So the likelihood of movement between two adjacent nodes of pixels, the cost of movement between them, and the suitability of a pixel as both a source and a target node. Okay. Now we can simplify those quite a bit by saying, okay, the suitability of a pixel of both as a source and a target is equal, right? Which in our situation makes sense because the habitat is the habitat. It's not directional necessarily. So you can reload that AOI if you need to. We have our patches data set, which will come into our restoration scenario a bit later. And then here, if you're, you can use those Q and R maps directly, or you can reload them after you save them. So just to reiterate, these are our maps that we're using. So whether you use the Q and R or if you reload those saved files, these will be your reference input maps. Okay. And now we get into the cool part where we have ConScape grid and path creation.
Just a quick, I guess, conceptual question. When would the path source and the path target an application of that?
That's the target. The first thing that kind of comes to mind is if you're modeling like in an ecological sense, maybe like one directional migration, where like, okay, I want to know I have this herd of caribou and I want they migrate this to this area in the wintertime. How is that? Yeah, how likely are they to leave from certain places down here versus arrive up here?
So would that be two different layer inputs that you put in, or that just affects the quality? Like, how does that implement?
I'm not sure off the top of my head. I'm sorry.
Because that might have the directionality we're talking about.
I think that's possible in the program. I don't know how to do it though.
Okay.
Any other questions before we keep moving? Okay, so first step is what they call ConScape grid creation. So this is kind of like an adjacencies matrix that we're talking about, where you're calculating ecological costs between these cells. And so we have all of these here, these inputs, affinities, sources, targets, costs. Those are all possible differential inputs that you can put into ConScape. But it is optional, as you can see, because we have our habitat map for all of them. And then we define, basically generate our resistance map within ConScape rather than inputting it using this cost function here. So if you remember this 2 minus x times to the log 10, that was how we generated our resistance map. Right? I just did it earlier so you could visualize. Okay. And then the fun part is generating the H grid, and this is the most computationally intensive part of the situation. So this is generating the random shortest paths. So that's what this grid RSP function is, where you need to import your G grid and then set your theta. So that is, we took an intermediate value here of about 0.5. Next. And now we can move on to mapping our functionally connected habitats. And this is where that alpha value comes in. And how that works is they take those distances and they transform it into a proximity, which is how using that transformation function, which is scaled by alpha. And there will be a tutorial on that coming later. But for now, we're using this 1/75, which is like 0.01 something, which is relatively generous in this situation.
Especially if you sell size, it's either,
Yes,
and then you do that, and so it's kind of 75. It's
Yes.
gonna be very, very large scale. Oh, anyway,
not huge. The one that they suggested for their, like the maps they used in their tutorial, which were 1,000-meter resolution, was like 1/50. So it's comparable. It's big, but it's not outrageous. Okay. And so the function that you use to calculate functionally connected habitat is this right here, ConScape R connected habitat. No, don't search. And then you import your H grid is the main variable that you're running this function on. And then you set your alpha, and that's where that runs. And then it's nested within this ConScape R match or rast, because ConScape, all of the rasters are basically matrices. They're called sparse matrices, which help them run faster. And it's an object type that R can't handle. And so what we did here is we, in this outer step, is we're taking that matrix and converting it back to a raster so we can look at it and play with it in R.
could you explain what the double column means? When you have
yes.
ConScape R and then a double column maps to raster, that means the function maps to raster, map matrix to raster of the package ConScape R.
Yep. So like, for example, the filter function from data flyers, it would be like data flyers DPLYR : select. And that's telling R like, hey, this select function we want to use from this dflyer package. And particularly when coding on like a server or something, or when you have lots of packages loaded that maybe have like similar names, specifying the package is good practice. And also it helps people when they're trying to use your code to know where those functions come from. Okay, so that functional habitat map looks like this, and that's the same one that I showed you earlier. Okay. And now we're going into quantifying functionally connected habitat. So it's like we have these, this legend here that goes up to 1,600. How do we make some meaning out of these scores, these units that don't make much sense to us? And quantifying functionally connected habitat is kind of a way to do that. Okay, so what you can do is you can sum the pixel functionalities to get this landscape level functionality, which is based off of this reference here. And then if you take the square root of that number, you can compute the amount of functionally connected habitat. So again, it's still in those comprehensible units. But
So that's the equivalent in connected area.
Okay. So then, if we basically take that value and then divide by this sum values have, so basically if so if everything was perfect habitat, right, we can take that number divided by the other and then times 100, and then we can basically compute a percent. So this habitat loss in this landscape is about 54%. And that's not to like a pre-colonization reference condition. That's just if the entire study area was ecologically perfect, right? Which
is a maximum habitat quality and everything is connected.
Exactly. Yeah. And if you reverse that, you can take the reference connected habitat, which is just 46%. So together, those values will add to 100%.
like how much of potential that you could reach
Exactly,
is we achieve.
yes. All right. So yeah, there's a little explanation here. This value would be 100% only if the entire city area had maximum habitat quality and it's perfectly connected, which is not a realistic scenario in any world, but it gives you some, it makes landscapes comparable between scenarios, which is good. Okay, so now we have a little scenario modeling exercise where we have our two patches. So we have patch A in the north, which is kind of a long, skinny corridor style project versus an absolutely massive square patch in the southern area there. Okay. And yeah, this is just an exercise. It's not realistic at all. I just drew these patches, obviously in ArcGIS with a square tool and just loaded them in. And I'll show you kind of how that works. So just to give you some context here, the patch A corridor is about 6 kilometers wide by 84 kilometers long. So even though it looks small, kind of on here, it would be like a massive project. And I think it crosses some major highways towards Medicine Hat. So
That is design means like you're improving that, you're restoring that.
yes, I'm getting to that. Yeah. And to give you an idea of the area, patch A is about 35% area of patch B. So it's patch B is huge. So now we want to say this scenario. Okay, if we restore patch A to 100% natural conditions, which is not realistic, but let's say we can. Now, let's say how much does functional habitat improve under that scenario? Okay, and so for the sake of time, I don't show you here, but all I did was for each of these habitat maps, I set, or for habitat quality, I set inside that patch A equal to 1. So it is now perfect habitat in that little rectangle, and there's absolutely no resistance in that rectangle. And then we basically just rerun all the steps we did before, labeling them with an A. So we create our ConScape G grid, call it GA. We create our random shortest paths, our H grid, I would call it HA, and then our functionally connected habitat from A. Okay, and again, using the same data, the same alpha and everything. And if we take a look at that functionally connected habitat map, we now see that we have this nice corridor that's connecting this southeast area to this kind of larger patch up here. Okay. And then we'll do some big comparisons. Oh, sorry, here we can calculate functionally connected habitat in this situation, and we get 49%. So it's a slight increase. And now we're going to go into patch B, and then we'll compare all three side by side in a moment. And so we basically perform the same methodology for patch B. We inside the patch, you set habitat quality equal to 1, and perfect habitat. There's no resistance. Sorry to all of the people and farmers who live there. You've now been ecologically restored. And then we rerun, create a new G grid, we create a new H grid, and then we recalculate functional connected habitat, and we see this big square here that has somewhat connection, but not super great. Okay. And then we can calculate our patch B connected habitat, and oh my gosh, it's the same increase. So still 49%, which is an increase from the reference, but equal to our patch A. So now let's take a look at all three of our situations where we have our reference, which is the first one we did. We have our patch A, and we have our patch B. And one cool thing you can see here is that we have a little bit darker area here. And then once it's connected, this whole area brightens up a little bit. And obviously here you have a mix of some kind of blue, light blue, dark blue. And then once this is restored, we see a little bit more function here, and it brightens up to green a little bit. Okay. And then if we compare our percent connected habitat, reference connected habitat, 46%. And restoring patch A and patch B both increased it to 49%. So you can see that it's a pretty, these are massive restoration efforts, and they only restored like 3% of functionally connected habitat. So this metric, I think, is a bit conservative, but it's kind of cool. And it shows, I didn't want to use this in case people are going through this and thinking, oh, a big patch restoration is always better or always worse than a corridor project. So it really depends on your scenario. So I don't, I was glad that they both came out to 49%. Because even though this patch A is much smaller than patch B, it still increased functional connectivity by the same amount. So I think that goes to show the power of corridors. But again, it depends on your context. So, a corridor is always better than no corridor, but it's not always 100% better than a big patch necessarily. So you guys are ecologists, you'll have to figure that out for yourselves. And I have 2 minutes left, which is great because we just entered the optional sections of this. A little bit of code to output all of your functional habitat maps together, and then a bit on computing the movement flow maps. And I showed these, it's just ConScape R function called betweenness k weighted. So this, it's a movement flow that's weighted both on the proximity and by the quality of habitat, which is what you want. And then this map to RAS function again to convert it to raster. So we change the coloring a little bit and we take a look at all 3 of our scenarios here. And we can see we have our nice big corridor up there, and then a little bit for our patch B as well, which is great. Okay. Yep, and then you can output those and references that I recommend that you check out, as well as the ones that I cited in this notebook. Okay. And with that, I'm officially done. It's 4 p.m. Those of you who want to ask questions and stay a little later, that's great. But we have some closing remarks that we need to get to, right?
Well, I think we need really thank you. Keep in mind that Celia did her PhD not on connectivity modeling and joined this program in January. And now run this case study co-designed it without her to run it and develop these materials for you. I think this is huge, and you did a great job presenting this. So thank you so much, Celia.
Thank you.
In terms of closing remarks, is Alvin there or not?
No, he's wrapping up another meeting right now,
Yeah, okay.
so he won't be able to give closing remarks.
Okay, so then we will still be around. Anybody have questions and so on? I said hands over. You didn't get to run this now, but you should have everything you need to try to run it. Are you going to offer another office hour next week? Or?
Yes. So some of you probably saw that I scheduled a meeting early on Monday. So it was optional. If you can show up and you needed help installing things or troubleshooting, I was there for you for that. And I will have another one next week. So, and if you need some help, you can email me. Outside of that, within kind of a week window, I'm open to setting something up. But after that, I'm cutting you guys off. No more help.
Yeah, starting a new job instead of being like,
Yeah.
all of these questions.
Yeah, exactly.
Yeah.
But if you want some help troubleshooting now for a few minutes at the end, I'm happy to help.
And then we will update this like by January at the latest.
Yes,
Okay, yeah, I was gonna ask about that, tutorial or worksheet.
for the alpha.
Yes, yeah.
Yes, it's almost there.
Okay.
Yeah.
Is that something you'll be distributing? Or is that?
So that is something we can make available with the materials for this project, I think, either posted on the ABMI website eventually.
Yeah, eventually it will go there.
Yeah.
If this is relatively still, I mean, whenever that comes out, I think this group would be interested. So
Yeah.
we could probably send it out to all the participants of the
Yeah.
afternoon at least or the workshop.
Yeah.
To alert them, and then we'll have a link where to find it. What's your job?
Oh, yeah. So it's another postdoc at Trent University in Peterborough, Ontario. which is, you know, it's a relatively smaller town, like 2 hours or so east of Toronto. And I'll be working, it's funded through the Ministry of Natural Resources, in collaboration with the Mishwakotton First Nation for woodland caribou conservation and modeling. So even though I'll be based over in Peterborough, which is way east, our field site and our study area is like right over Lake Superior, kind of Thunder Bay, Wawa area. And primarily looking around the lake for woodland caribou habitat, and as well as Mishwakotton Island in Lake Superior, which is kind of cool because you have that like a real life experiment with the caribou on the island. And yeah, so it'll be doing a lot of habitat suitability modeling, some connectivity modeling, which is kind of cool because ConScape was originally designed and tested using reindeer in Norway. So I was like, oh, perfect. Caribou are like the same thing. It's fine. Yeah, so that's exciting. And I'll be getting to do work with Mishwakotton First Nation, so they'll own all the data and stewards of that. And we'll really get to tailor the project to their needs, which is really cool. Thank you.
So with that, we want to thank again all our speakers. So we also have to leave Dave, I don't know, everybody back in there.
Yeah.
Any problems?
Dino and Tracy are the other.
Nino and
Tracy,
Tracy, still here, and Celia, Alvin couldn't join anymore. And then again, thank you so much. Samantha, for
Yes,
the
a round of applause for Samantha. Really took on all of the tech challenges, which you can see were numerous.
And thank you to all here in the room and those online have gone through the whole day with us. I'm sure your heads are about to explode. But you have some, things you can go back to. The slides will be again made available, and we'll send you a link where you can find those things. So hopefully this has been helpful for you, and there'll be some of these resources hopefully will help you do some good stuff in your realm of the world. Yeah, sphere of influence, and that's how we go.
Thank you. Thank you.